Our next presenter is Tim from ChemAxon, and some words about him. He completed his PhD in biochemistry and spent years in the biotech industry. And today he's the owner of the Informatics Matters Ltd. So
welcome everyone, I'm Tim Dudgeon. Today I'm giving a talk entitled Making Development of Chemistry-Based Applications Easier. And I think you'd all agree that would be a good thing. Before I do anything, let me acknowledge the people who've done all the work here. It's primarily been these guys, chiefly Gustavo at the top. So the aim here was to explore some of the modern web development techniques and see how they could be applied to building chemistry-based systems. What I'll be talking about is building a web-based system, because that's probably the most interest to most people, but a lot of what's covered could also be applicable to non-web-based systems as well. But basically what we were trying to do was it was basically an experiment to see how modern development techniques could be applied to developing a chemistry-based system using Marvin and JChem. Basically, we wanted to look at modern languages, modern frameworks, and things like that, and see to what extent we could use those in sync with Marvin and JChem, and let the frameworks do the heavy lifting, and let us be as lazy as possible and write as little code as possible to develop the application. Also, one of the key aims was to really try to get real code reuse. Really start using component-driven development. And also, one of the key things we were trying to do is insulate ourselves from the chemistry engine implementation, so that we could switch implementations if we wanted, and that the developer did not really have to need to understand the nitty-gritty of the implementation details of the chemistry engine. And basically, I think it's fair to say that modern approaches don't really come close to this when you're developing chemistry-based systems. And our aim, the aim of this experiment, was to find out whether we could improve on this. So basically, this was an experiment. I'm sure you agree that it's probably more amusing to hear other people's mistakes than your own. So I hope you might enjoy some of the experiences here. So that's the aim. Let me position things a bit. So here is an example taken from the JSP example, which is included in every JChem distribution. And here we've got the Marvin sketcher. We've got a panel here that displays some search options. And there's code taken. I should warn people, there is code shown in this, so chemists might want to look away at appropriate intervals if they're feeling sensitive. So Marvin sketch is put in the web page. You're basically using a JavaScript call like this. And this is really quite a nice way of doing it. The JavaScript isolates you from the implementation details of the applet, so that if the applet details change, as they did do recently, basically the JavaScript library that is used can accommodate that, and you upgrade JChem and nothing changes. The applet still works. Contrast that with how these options are displayed. These are the search options. And here is just a tiny little bit of the code that is writing out these options. And there's a lot of complexity here. Firstly, understanding these options is far from straightforward. It's pretty complex to know which options should be available for which search types and which table types. In fact, Subalch is probably the only person who really fully understands this. And so writing out this as a traditional HTML type approach is really not a good solution. So the sort of things we're trying to do in this case maybe would be to make this as a component that we could reuse in multiple applications. Another example, if you're writing an application that's writing structures to a database, you need to handle persistence. And you've probably written a DAO, a data access object, that does that sort of thing. Here is a tiny snippet from a DAO, actually one we wrote as part of this project. which handles the low-level updating of structures in the database in this case. There are various problems with these sorts of approaches. Firstly, you need to write tons of code to get all this done. Secondly, within that code, there are a lot of traps. You've really got to know what you're doing, otherwise you can run into problems. Some of these are straightforward problems, like remembering to close your result sets and your statements and things. Some of them are less obvious. Because there's lots of code, you really need to test pretty extensively to make sure everything works correctly. And it's not easy to test because of the architectures and things like that. Another thing is difficult to refactor or upgrade the applications. If we went back to the previous slide here, if there was a new search option created in a new version of JChem, you have to go in and update this code to actually make that search option available. So it's hard work from that point of view as well. And basically, because of all these problems, the general approach, I think it's probably fair to say, that's been taken is copy and paste programming. You find an example that works, you copy and paste the code, and you modify it to try to get it to work in your case. And that's really not a good approach to producing robust systems. Another real problem is you really do need specialist knowledge to build these systems. You've got to understand what all these options are and how to use all the JChem libraries and things like that. So you've got to have developers who understand the JChem and Marvin stuff pretty well in order to be able to build these systems. And, of course, any code you write is going to be pretty strongly coupled to that particular database and that particular chemistry engine, whether it be JChem base, whether it be JChem cartridge, or whether it be someone else's cartridge. So what we are trying to do is try to avoid those sorts of problems. A very quick history here. Building web-based systems with Java really started back in the very early days of Java when once JDBC and JSPs were available. And originally, they were done in what is known as the Model 1 architecture, where everything was put into the JSP. And that's really a pretty lousy architecture. You had JDBC persistent code mixed up with your JSP presentation code and things. It wasn't a good solution. It was a real code mess. Quite quickly, an architecture known as Model 2, or Web Model View Controller, came along, which had a much better architecture for doing this. And Struts was the paradigm for that, the Struts framework. And probably more applications have been written using Struts than any other Java framework, web framework. It was a big improvement to the architecture, but there was still a lot of problems. It really suffered from configuration hell. This came from the early days of the EJB specs, when everyone thought it was a good idea to write lots of XML to configure things. And you spent all your time writing XML, not actually writing any useful code. Over time, those frameworks have improved. Struts itself has improved, but also newer frameworks like Stripes and Spring Model View Controller and things like that. They make use of more modern approaches, such as configuration over convention and dry, meaning don't repeat yourself. So these frameworks have improved, but they still have some limitations. And also, in parallel, some more object-orientated frameworks have cropped up within the Java community. GWT from Google and Wicket are two good examples. In addition to this, the outside world was changing as well. We tend to be very Java-focused here, don't tend to look outside the Java world too much. Well, we should do. While this was going on, something was happening. Ruby on Rails was really setting the new standard in how web applications should be delivered. Ruby on Rails was a complete application stack designed to handle all layers of the application. It built very extensively on configuration over convention over configuration, get it the right way around, and don't repeat yourself. And it took real benefit from the Ruby language, which is a much more productive language than things like Java. And also older languages such as Python and PHP, they're also doing things as well. There's some quite good frameworks available in Python. And more recently, there are a number of newer frameworks for new languages on the Java virtual machine. Of particular relevance are Groovy and Grails and Scala with its Lift web framework. So there are lots of new things happening outside the strict Java world as well. Another quick thing here about languages on the JVM. Again, we tend to be very Java-centric and think only about Java. But over recent years, there's been a big evolution in languages on the Java virtual machine. And new languages have come along. Groovy, Scala, Clojure, JavaFX, as well as other languages such as Ruby and Python being ported to run on the Java virtual machine. And many of these languages are more productive. More fluent is often a term that's used. Many of these languages are dynamic rather than statically typed, and some of them are very good for writing things like domain-specific languages. So there's a lot of evolution going on in the language area as well, which means maybe Java isn't the right language to be using. And now the JVM, the Java Virtual Machine, is really the heart of the ecosystem, of the Java ecosystem now, not really the Java language itself. And I point out particularly, I think, Groovy and Scala, which I think are two languages that will be of particular relevance in future years for this community, largely because they are so tightly coupled with the Java language. They sit really well and really nicely with the Java language, but will provide better productivity, while at the same time you're retaining all the benefits of Java. So basically with these frameworks, it should be possible to get more for less. The framework does the heavy lifting for you. It'll handle the persistence, it handles query, it handles things like AJAX and web services because they're built into the framework. You don't have to develop things like web services and AJAX, you really just have to turn them on. I'll just comment here that it is a confusing area. There's so many damn frameworks for all of these things that it can be difficult to choose. And this is one of the biggest problems, how to choose which are the right ones. We've made some choices. I'm not necessarily saying what we have chosen are the right solutions. They're just things that work for us. So, how do standard systems work? By standard, I mean non-chemistry. Well, most standard systems have data that's pretty simple. They handle things like bank accounts, purchase orders, catalogue items, flights, addresses, things like that. And because that data is very simple, it maps very, very easily to a relational database. The persistence tier has basically been automated by object relational mapping tools that handle all the CRUD, that's create, read, update, delete operations, and the query operations. So the persistence tier, the framework, handles all of these things for you. And basically, I think it's fair to say that if you were building a system nowadays that handled purchase orders or flights or something, you really wouldn't even consider building it without an ORM tool. But chemistry is different. It seems to be stuck doing it the old way. Things are lovingly handwritten, like longhand, and that results in relatively poor productivity. Why is this? And can we solve it? So what makes chemistry difficult? Well, there's really only one reason. It's because molecules are very complex. They don't map directly to relational databases. And so things like the CRUD and the query operations cannot be expressed as simple query, and so can't be generated using SQL generator frameworks such as the ORM tools that I was talking about. What you need is a chemistry engine to help. Now, our engine is JChem. There are obviously others out there as well that could be used. But basically, you need a chemistry engine in order to support the persistence and the query of chemical structures. And that, as a result, that has meant that chemistry-based systems are still mostly JDBC-based. They're mostly JSP or a variant of JSP. They're mostly handwritten. They mostly use copy and paste code from the working example you found earlier. They make very little use of components. And you need to have a lot of code to really deliver the functionality, and they tend to be difficult to upgrade, refactor, and to test. But does it have to be this way? And this was our experiment. So we wanted to look at, are there benefits in languages other than Java? Can persistence frameworks be used with JChem despite those problems? Can we use modern web frameworks? Can we get real code reuse as opposed to having to copy and paste everything? Can we get real independence from the database and from the chemistry engine? So the aim is to exemplify building this using some best-of-breed tools. This is basically the example system that we built. It's a sort of a very simple suppliers database where we've got a number of SD files we wanted to import into a database. There are basically 3 levels in the database. There's the structure, that is a unique structure. There's a sample, which is basically an entry in each of the SD files. So where a structure is available for multiple vendors or even multiple times within the same vendor, you'll have a many-to-one relationship there. And each sample is related to its source, which is basically the file it came from. And so this is the web application we built. I'll demo it at the end if I've got a bit of time. And we tried to build this using a modern web framework and using a persistence framework. How did we do that? Well, this is the basic architecture of the system. At the bottom tier, you've got the database, you've got the JDBC driver, you've got the persistence layer. Then on top of that, there'll be a classic service tier. And on top of the service tier, you can expose that functionality either through a web model view controller type architecture, controller tier and the web tier up to a web browser, or you can expose it as a web service and then consume it using any language you might want. In terms of what we use to implement this, the database, again, could be anything. In the example, it's Derby, but it's completely pluggable. The persistence framework we're using is Hibernate, and Hibernate using JChem to manage the persistence. And the web framework we're using is Wicket, and Wicket is obviously using Marvin for the display of the structures. So the ideal situation, meaning non-structural information, we've got 2 entities in our system, the source, which is basically who the compound comes from, and the sample, meaning how much of the compound there is and what its code is and things like that. This code is Groovy code, written as if it's a Groovy and Grails application. I could show Java code instead. Exactly the same would apply. It would just be 4 or 5 times as much code, so this is easier to show. So for the non-structure stuff, it's really very simple. You define the properties of your source, you define your relationships, and then at the end of that, and once you've done that, the framework, the Groovy and Grails framework, can let you do things like this. Def s equals sample, find by code, give it the code, and you get the sample, and then sample delete. Those methods we do not have to implement. The framework implements those methods for us. So all we have to do is define the entity and then use it. There's nothing else more we have to do here. But there's a problem here, obviously, with the JChem stuff, because this slide really explains it. This is an architecture slide stolen from the JChem website. And basically, what's happening here is when you do a query or want to insert a new structure or something, you're not talking directly with the database, you're talking through the JChem class library. And any ORM framework that is trying to automatically do the persistence is basically designed around generating SQL for you to do that persistence. But that won't work here because we've got to go through the JChem class library. So this approach, on the face of it, doesn't seem to work. For JChem Cartridge, it's actually a bit better, because JChem Cartridge, the situation is turned inside out in a way, so that the JChem part is actually moved inside Oracle, or inside the JChem server. The application can now talk to Oracle using plain SQL. But unfortunately, it's not standard SQL. It's got operators like JC formula, JC compare, and things like that, but it is at least SQL. And these ORM frameworks can be customized to a large extent in terms of how the SQL is generated. And here is again, a Groovy and Grails compound entity that is now configured to access a JChem cartridge table. And it looks pretty well identical to the previous one. This is the only bit that's different, in that we are now using the JChem functions to actually extract, in this case, the molecular formula and the molecular weight from the table. So basically, with JChem Cartridge, we can actually solve the CRUD aspects of the application relatively easily. Problem is, we're not solving query. Query still needs a custom implementation, but there is a solution to that. Named SQL queries are implemented by Hibernate, so we can use named queries. It's not a completely clean solution, but it works. So basically, with JChem Cartridge, we can end up with a solution that can use persistence frameworks reasonably easily. There is a problem, though, from my conceptual point of view. and that is that you're limited only to Oracle and only to JChem Cartridge. And I don't want to have those limitations. I want to be able to use JChem Base. I want to be able to use any database I want. So if you're happy to be limited to Oracle and Cartridge, this sort of approach can work. But we weren't satisfied with that. We wanted a more generic solution. And we wanted to find out whether JChem Base can be tamed and made to work with our persistence framework, Hibernate, and JPA. Let me say, I'm using the terms persistence framework, Hibernate, JPA, ORM a bit loosely here, and a bit interchangeably. So what we wanted to establish was whether the CRUD operations for structures can be performed, again, using pure persistence, pure JPA. Similarly, can we do queries in the same way? Also, quite importantly, can we do the same for DDL operations, creating the tables in the first place and things like that, which is often an important part of building an application. And can the developer work with all this in an engine-agnostic manner so that we can just plug it? We can plug in the cartridge, or we can plug in JChem Base, or we can plug in a Daylight cartridge. From the developer's point of view, they build the application in the same way. So that was our challenge. And the solution to it, basically to the persistent part of it at least, is basically the Hibernate event model. This is a set of interfaces here that provide hooks into the persistence mechanism that Hibernate provides for you. And you don't know if you can see this, but for most of these operations, there's a pre-listener and there's a post-listener. So here's a pre-insert event listener, and somewhere there'll be a post-insert event listener, post-insert event listener. So what this means, actually, before the structure or whatever it is inserted, you can hook something in to do something custom. And again, there's a hook for after as well. And so what we used is actually these hooks to actually just basically hijack the process so that we could intercept it and then use the JChem Base API to do the operations. So this is basically how it works. We start with the user requesting something like persisting a structure. And that notifies the bridge through this listener interface. The bridge then calls down to the engine, which is the chemistry engine implementation. That might be a cartridge, or it might be JChem Base. And the engine then uses its specific implementation, the JChem Base API or the JChem Cartridge SQL, to actually store the compound in the database. And it sort of goes like this. You start with sort of entity manager persist, and so basically this is the sort of the user or the developer saying save this structure. The pre-insert event listener intercepts that operation and says, engine bridge, do your stuff. I've been asked to insert a new structure. The engine bridge calls as the engine and says create structure. That uses the JChem API to load into the JChem Base table, and then when that's all done, the entity manager continues as usual and saves the entity using the standard JPA approach into a different table, which has basically a one-to-one relationship between them. So that's the approach. This is what the engine bridge looks like. The methods are hidden, but this is basically what the interfaces are: on pre-insert, on pre-update, on post-delete, on post-load. So these are the hooks into the system that let us load or save or delete the structures. And at the engine level, this is the JChem Base engine. This is how we would create a structure. Method called create structure takes the structure and the connection, do create structure, which is this method, which then looks like very familiar code to any JChem developer. Connection handler, it uses connection handler, update handler, and all that. But this is all handled by the engine. This is the library that we're using. The developer doesn't need to worry about this at all. The developer is only having to call that very first operation, and all the rest happens by magic as part of the library. So how would the developer use this? Well, this is our structure entity, this time written in Java. Again, most of it is just a standard Java bean with annotations JPA annotations to mark the fields appropriately, and some to define how it behaves as a web service. Of interest here is the annotation structure entity, which is one of our annotations that basically defines what type of JChem-based structure it is, what type of JChem-based table it is. So here we can say you can specify things like the absolute stereo flag, the standardizer, and things like that, what type of table it is. In this case, it's a molecules table, but we could specify a reactions table if we wanted instead. So this is how you define what your structure entity in the system. And then with that defined, you can just use the service. You can write a service that uses that to persist the structure. So we've got create structure here, takes the structure. We create an empty list if we don't have any samples for it, and we just call em persist, entity manager persist, and then the engine just handles all that persistence for us, and JChem base eventually at the bottom of the stack saves the structure into the database in the correct way. If we want to find the structure, again, we just ask the entity manager to find the structure for that ID. All of it, this is as deep as the developer has to get. All the rest is handled by the library. So what we found was that we could achieve this, and one of the real benefits is that we end up with something that is extremely pluggable. And to illustrate this is the only code change we need to make to change this system from using JChem base to using JChem Cartridge. We just change the class from being the JChem base engine to the JChem Cartridge engine, and then our system would be working with the cartridge and not with JChem base. What the developer has built would be exactly the same. The application would now just be using cartridge. Okay. Query, I haven't really got time to go into query because I'm running out of time, but basically also we've got a way of actually executing queries. They start at you define your query in the web page, it goes down to the service tier, and then it gets executed again by the engine. Web services, as I said, it's just a question of turning a web service on. This is how you do it. This is the configuration of the servlet. This is how this is the web service class which we're exposing, again using standard J2EE5 annotations. And to use it, this is the code you have to write. It's very, very simple. There's really no code you have to develop. You just turn a switch on pretty well, and you've got web services. Same with Ajax. So, does it work? Well, yes, it does. Have I got time to do a demo or not? It's only about one minute at most. So here's the system. This is not designed to be a fully fledged, exciting system. It's designed to be a prototype of the technology. So it's not a spectacularly interesting system in itself, but it does just illustrate that it actually works. So basically, we're running a structure search here. We're sketching it in our structure in Marvin. That should all be very familiar to people. We execute the search, which on this page, I haven't got my screen's too. It doesn't work on a small screen. No, sorry, I've lost it because of the. Yeah, I can execute the search, and okay, it's run. So here are our results. Click on that. Click on the structure. And you see the suppliers that supply that compound. This particular compound's available from Atava and from Maybridge. There are about 250,000 structures in this system. So a very quick demo just to prove that it does work, and this uses the approach that I've described. Okay, so I've pretty well finished. So it does work. So did we proceed? Did we succeed? With the persistence, yes, definitely. We got the approach that we think works. It's not fully implemented yet. There's lots of missing functionality, but basically the approach does work. We've created a meaningful web app that uses clean JPA interfaces, so there's no JChem code in your application, only JPA code. It's vendor agnostic, meaning we can plug out one engine and plug in another one. We could even plug in a non-ChemAxon engine if we wanted. In the web tier, we've done much less. And this is a bit more difficult because there are so many different web frameworks out there. It's difficult to know which ones we should be supporting. So we've done much less in the web tier than we have in the persistence. But the benefits of building things like web services and things should be obvious. So what's coming here? So this is an experiment. It's not ready for prime time yet. But what we hope will become available is this engine architecture and the implementations, certainly for JChem base and for Cartridge. We've also got a Groovy library that wraps various functionality in JChem and makes it easier to use in the Groovy language. There will be some web components for things like the structure display, structure search options and things like that. That can be real true components in your web page rather than having to write it or copy and paste it. Also, other suggestions are welcome. If you've got ideas for things that can be done in this area to make building your applications easier, let us know and we'll see what we think we can do. So what will become available? As I said, early stages of development. Initially, we'll probably be using these tools internally for creating our own systems or for consultancy operations. But they'll also become available as an extension to JChem in much the same way that the sort of web services stuff is available as an extension. And we're obviously actively looking for people who are interested in this approach and maybe wanting to explore it. Okay, so that's it. Thank you very much.